So I've been asked to speak about upper airways and non-invasive ventilation. Disclosure is the same as yesterday. So this is just to give you a little bit of background about the upper airways. They have many roles: humidification, speech, swallowing, airway protection, breaking of expiratory flow to main end expiratory lung volume. I'm going to focus on airway dilation for inspiration. Specifically, I'm going to focus on the laryngeal muscles because we just recently completed a study in newborn lambs comparing the upper airway muscle activity during pressure support, nasal pressure support, and nasal non-invasive NAVA, and the paper was just put on PubMed on Friday. So the important laryngeal muscles that I want you to know about for today. So if we're looking at the larynx, this is the front, the back. It's a superior view. And I'm going to talk about the TA, and I always try to say this thyroid muscle. I'm going to call it the TA. It's a constrictor muscle. And the cricothyroid muscle, which is a dilator. It's important for you to know that the larynx is actually a closing valve, so that, and based on its original function, which is defend the lower airways against potentially harmful intruders, when you think about non-invasive ventilation, you don't want those muscles to fight against the ventilator. And I don't know if you're familiar with these papers by Junio. It was a paired publication that was published in JP 95. It's an excellent studies that they did in healthy volunteers where they used a laryngoscope and examined the angle of the vocal cords with increasing non-invasive positive pressure ventilation. The first paper was done during awake situation and the second one during sleep. And basically what they found is with increasing levels of NIPPV, which is non-invasive intermittent positive pressure ventilation, they found laryngeal closure against the ventilator insufflations. And actually there was a linear correlation between the closure and the level of the assist provided. And this actually resulted in a decrease in lung ventilation. So you can imagine that all that air that was being delivered was probably being diverted to the esophagus. So we wonder about gastric distension, and we think about all the little babies who may, if delivering asynchronous ventilation, if they're getting gastric distension and therefore feeding intolerance because of asynchronous non-invasive ventilation. So Jean-Paul Pro, who is a colleague of mine, excuse me, from Sherbrooke, did a study in chronically instrumented newborn lambs. These are not premature lambs, they're term lambs, and found when he looked at the EMG activity of the laryngeal muscles, with increasing non-invasive pressure, positive pressure ventilation levels, he found increased activity of the laryngeal constrictor muscle. So he's looking at not at a closure or a visualization of the vocal cords, he's actually looking at the activation. And he saw active laryngeal closure against ventilator insufflations. This is some tracings from that study. Here you have the electrical activity of the dilator muscles. This is the electrical activity of the constrictor muscles. This is the diaphragm electrical activity that he measured with needles directly on the diaphragm. So, well, you'll see next slide how we did our thing, but this is a chronically instrumented animal. We used a nasal mask. The mouth was not covered by the mask, and we were able to measure mask pressure. We measured the pressure directly. They measured pressure directly in the trachea, and they measured lung volume with the respiratory bands. And you can see here with just a CPAP, which is not a triggered device, that when you have, I'm just trying to see if you mark, yeah, during inspiration, so this is the inspiration part here, that you have no constrictor activity and you have dilator activity as expected. However, when they did pressure support in these newborn lambs, what they found is that during the inspiratory period, so you can see here when the mask pressure was increasing, that there was actually increased activity of the constrictor muscles. So these animals were actually fighting against the ventilator and attempting to close the glottis. Just a reminder, I showed this slide yesterday. If we look at the timing of the diaphragm in terms of when diaphragm motor units start to be recruited, this is human data, and you look at another upper airway muscle, which is the genioglossus, you can see that the upper airway muscles are actually activated slightly before the diaphragm. And that makes total sense. You want to activate your upper airway dilator so that the airway can be ready for when the diaphragm is going to be activated to draw in the air. And when I saw Jean-Paul's paper on PubMed, I immediately wrote him an email, and I thought to myself, oh my God, I bet you we won't see this during NAVA. And he wrote me back about 15 seconds later and said, yes, yes, let's do the study together. And the whole hypothesis was based on the fact that if you have the brain controlling the diaphragm and the ventilator at the same time, and we see this slightly pre-activation of the upper airways, it might be that when you apply synchronous non-invasive ventilation, that you won't see the fighting of the constrictor muscles. That was our hypothesis, and we set up a study that we did in Sherbrooke. I'll tell you about that. So our hypothesis was that non-invasive NAVA, offering a more physiological approach, meaning timing with the upper airway dilation, to assisting ventilation would prevent activity of laryngeal constrictor muscles compared to non-invasive pressure support. This is the experimental setup that we had. We had a lot of difficulties merging our two systems. So the lamb is awake and non-sedated and sitting in this little hammock here. This is Jean-Paul Pro's system in Sherbrooke, and this is the Servo-I and our acquisition system. So we spent the good first day and a half, and Norm actually did a lot of work on trying to get the two systems to speak to each other. As I mentioned before, we were looking at chronically instrumented lambs. Everything that he measures by telemetry. But basically what we did was we measured the EMG activity of the TA and the CT. We measured the diaphragm electrical activity with our esophageal catheter, but he also implanted needle electrodes, so we have the costal diaphragm EMG as well. We have states of alertness because we did polysomnography. Tracheal pressure and tidal CO2, respi trace, everything you can imagine we basically measured. And this is just to show you that this is at the time where they had a lot of this hoof and mouth disease, which required us to wear biosafety suits. And that's just to tell you that's a little bit different from foot in mouth disease, which is what I have a tendency to have a lot of. Anyhow, we had to do the full gear, and they had to plan the delivery of the lambs when we were there, and it was a really good trip. The experimental design is here. So after day one, when they chronically implanted the measurement devices, day two was the day, for the chronic instrumentation. They allowed 2 days for recovery after the surgery, and then on day 5 is when we tested them. And what we did was increasing levels of nasal pressure support. So we did a period of CPAP before with no pressure support. Then we did pressure support of 10, 15, 20, and then we did 3 NAVA levels trying to match those peak pressures. Initially, we wanted to look at the periods when the animals were awake, except that the animals kept falling asleep, and we were banging and making lots of sounds in the lab, and we just couldn't keep them awake. They were so comfortable in the hammock. So we decided, because sleep state affects all this, so we decided to look at just the quiet sleep periods, and we got a lot of those. So these are the results. Again, you have the constrictor muscle activity, the dilator muscle activity. This is the diaphragm activity measured with their diaphragm needles. This is the EDI catheter signal, the mask pressure, tracheal pressure, and tidal volume. This is during spontaneous breathing. This is during pressure support, and we were able to reproduce their studies and show that during inspiration, the constrictor muscles are active, indicating that they're fighting the ventilator. Interesting is you can see how silent the diaphragm has become at these high levels of activity. And then when we put them on NAVA, you can see when we tried to match the same pressures in the mask, which was actually very difficult to do, you can see here that we did not observe any of this constrictor activity. And actually, we studied 8 lambs in total. So after Norm and I trained them on the first 2, we left them alone, and they did the rest of the studies on their own. And you can see here, when we look at the this little plus sign means that we observed the constrictor muscle activity. So in 4 out of 8 at pressure support of 15 and 5 out of 8 at pressure support of 20. And you can see here that even at the 3 NAVA levels that we looked at, we never observed fighting of the ventilator during the non-invasive NAVA. And you can see here, just to show you what the impact of this glottal closure is, you have here the mask pressure in the red tracings and the tracheal pressure in the blue tracings, and this is with the mouth closed. So you can see here how much of the pressure is actually not being transmitted to the trachea when the glottis constrictor muscles are active. And you can see that during NAVA, the airway, the mask pressure and the tracheal pressure matched, even at the same level of high pressure. So in conclusion, nasal IPPV, so pressure support volume control mode, can trigger active glottal closure, which opposes ventilator insufflations. This results in a decrease in lung ventilation and may actually cause gastric distension. Contrary to pressure support, increasing levels of nasal NAVA should be never induced an inspiratory active laryngeal closure in the newborn lambs. So we want to know, in terms of the future studies that we're going to do, is it due to the synchrony in itself, or is it actually due to the rate of the rise in pressure? Because I showed you that in pressure support, the pressure shot up, or is it because it's just a more physiological development of the pressure? So if we had a neurally triggered pressure support, we would be able to answer our question at that point. And so here are my acknowledgments. Norm, big thank you to you for doing all that work. And that's the team in Sherbrooke. Thank you.